Thank you so much for having me. Thanks for coming out. Thanks for waiting until the end of the day. I realize I'm all that stands between you and what I can only assume is a happy hour, so I will go as quickly as I can. So the title of this talk, Building Resilient Systems with Stacking. I have to be totally honest with you and say that I would say, a crisis of faith about the title of this talk after I gave it, or presented it. One of my friends actually misheard me when I said the title, and they thought I said breaking resilient systems with stacking. That sounds way cooler. We're not going to do this, unfortunately. Given the whole discussion around Phoenix not being your application, I think one of the titles presented was, is stacking my application? And then if I was going to pick a title now that more accurately represents what I want to talk about, I think I would title it simply, How to Boot Your Applications Correctly. Not as exciting as maybe building resilient systems, but hopefully you will all bear with me. So what this talk is really about is scaling. And when I talk about scaling, I don't mean this, the now infamous road to 2 million WebSocket connections. I'm sure we've all seen this. But by and large, the scaling that we're talking about here is really the beam. The beam is what allows us to do these kinds of things. And because in reality, the beam is sort of the fulcrum upon which we'll place the lever in order to move the software world. The beam gives us all this great power, this great tooling. And so in a lot of cases, we get what we consider to be scaling for free. That's not exactly what I want to talk about. Instead, what I want to talk about is this word, resilience, and what that kind of means for us as engineers. So resilience is defined as an ability to recover from or adjust easily to misfortune or change. And I love that term, misfortune, because how many of us resonate with that at 3 in the morning when the pager goes off about how unfortunate we all are to be in that position? There's a great paper. Really, I highly encourage you to go check this out. If you take nothing away from this talk, you could walk out right now, but remember this paper. It's really, really good. And it's simply titled, How Complex Systems Fail. And it's a treatise of about 11 or 12 bullet points about the nature of complexity, the nature of failure, the nature of building systems that cope with failure. It's actually, interestingly enough, written by someone in the medical profession. And what they're talking about is medical technologies, but it deeply applies to aerospace, utilities, these large-scale sort of interactions between incredibly complicated things. And I think there's bits of it that really apply to what we do. And the one that always sticks out to me, the one that really, really resonates with me, is this point here. Complex systems run in degraded mode. So let's break that down. And I realize this is a lot of text, but I'm going to quote it because I think it's so good. Complex systems run as broken systems. The system continues to function because it contains so many redundancies and because people can make it function, despite the presence of many flaws. System operations are dynamic with components organizational, human, technical, failing and being replaced continuously. That deeply sums up my life. I think what this gets at is like the heart of the problem, right? Like everything is always going wrong. At scale, everything 100% of the time is going wrong. And your job as an operator, as an engineer, is to figure out how to keep things from causing catastrophic failure, meaning failure that happens when more than one thing happens at the same time, when more than one thing goes wrong at the same time. So we've defined resiliency, and we're talking about systems, and because I come from the school of closure, I've learned that every good talk starts with definitions of words. So we're going to also define system. And a system is a group of interacting, interrelated, or interdependent elements forming a complex whole. Said a little bit differently, systems have dependencies. Systems rely on other systems. They rely on other systems that rely on other systems. It's sort of systems all the way down. And if you think about your textbook application, you might have your nice Elixir code running on the beam, and that has to interact with some sort of web server. Maybe you're using Cowboy or Ellie or something else. You also are going to depend on some sort of database connection, probably. You might have some sort of cache, like a Redis, thrown in the mix. You might need to talk to some sort of queuing thing like Kafka because you're in the Web 2.0 startup world with cool toys. And all these things your app depends on in order to provide a useful experience to the end user. And of course, those things are complex systems in of themselves, right? So they are relying on things too. You know, Kafka is actually just a bunch of files and a zookeeper, which who knows how that works. And databases, they're dealing with files and buffering and B trees and IO and all kinds of nonsense, threads. And in order for your application to work correctly, it needs to work in concert with all of these things. So it's really more fair to say that our app isn't this thing in the middle. It's actually better to draw a whole box around this thing and say that that is in fact our application. That's our service. Our service is dependent on all these other different components. Of course, it doesn't really end there because it's systems all the way down. In our app, if we're working in some sort of, I don't know, let's say some sort of architecture that's oriented around services, some of them you might even call micro, you have a whole bunch of other things that might talk to your application. Scaling, when it comes to these sorts of opportunities, is a problem of handling failure. Most often, scaling is not CPU. Scaling, it doesn't really matter that much how fast, how much computation you can get through your VM. What matters is how you handle failures. And I contend that this is why Erlang is so good at scaling. Because what it allows you to do is handle failures gracefully and degrade your experience in nice, well-understood ways. Another important point here when you talk about failure is that failure is not really determined by your service. Failure is determined by your client, whoever's calling your service. For instance, if we have some client who makes a call to our application, we need to make some downstream call to some other service. This doesn't have to be a service. It could be a database call. It could be any sort of dependency that you have. If that call is good, then our call can be good and we can return that back to the client. However, if a client makes a call to us and we make a call to another service and that call does not go well, what do? Well, we might need to surface that error back to the client. The point here is that the client is who determines whether your request was good or not. You don't get to determine that necessarily. This is not a scenario that's limited to microservice architectures or any sort of big architectures. This can happen in your monolith. The probability of it happening when you have lots of services obviously goes up, but we can experience these things in all kinds of different avenues. Dependencies are also more than just your other systems, and this goes back to that quote we read. Because the thing that keeps your service running, the most useful thing that you have at your disposal, the thing that truly, truly keeps the ship afloat, is humans. It is all of us in this room who are up at 3 in the morning when the pager goes off that are keeping the service healthy and keeping the service running. And we need to treat those humans as first-class citizens inside of that system. There's only so many problems Kubernetes can solve for you. Humans are not one of them, as it turns out. Although they're probably working on it. There's probably some new stateful set thing. Enough YAML in the world, we can make Kubernetes work. All right, so systems should do a couple things. Systems, one, need to handle failures gracefully. They need to provide feedback to other systems, and they need to give insight to operators. And that third point is really, really key, because those operators are what are really saving you at the end of the day. So what we're going to do is in order to kind of service all of these goals, there's been a couple things that we've been putting into place at Bleacher Report where I work, and I'm going to talk a little bit about how we do that. So what we're actually going to do is we're going to take all of these ideas and we're going to think about how they stack together and what we call this sort of stack design. This is not our term. We've stolen this from there's some good prior art out there in the ERLANG world. But this is kind of the big concept. So specifically what we're going to talk about, we're going to discuss booting your runtime and configuration, starting dependencies, connecting to external systems, alarms and feedback, and communicating with services we don't control. So let's dive in. So booting the runtime and configuration. So we'll start with some server somewhere. Oh, sorry, that was probably really gross sounding. My bad. We'll start with some server somewhere, or more likely these days, we'll start with some Kubernetes somewhere. There's one sort of infallible rule of the universe at this point, and it's that if you're not going to run Kubernetes, someone else is going to run Kubernetes for you. Your box probably ends up in a Kubernetes at some level. So we'll just say there's a Kubernetes. And what we're going to do is we're going to put our release on Kubernetes. So going back to our application, we need to find a way to box this thing up, and whether it's building a release and putting that into a Docker container or however you want to do it, or putting that release onto a box, it kind of works out to the same thing. And the most important point here is that releases are the unit of deployment in Erlang and Elixir. There's a bunch of really good reasons you want to use them. They allow you to really understand how your application is going to boot and the order it's going to boot things. It helps you understand configuration, although that's been contentious in the past. So, but by and large, releases are the unit of deployment in Erlang and Elixir, and we want to be using them. We use Distillery, as you should. There's really not a lot of other options, so that's what we all should be leading into. The question we want to ask ourselves at this point, though, is what has to be here to start our application? That's the first place. That's the first thing we're going to do. So if you think about the sort of timeline of how we're going to boot our application, the first thing we want to do is read in system configuration. This is going to allow you to configure things like SSH and sort of internal Erlang stuff that you don't necessarily get access to at runtime, that needs to be configured prior to starting the beam up. We're then going to start the beam. Once the beam's up and running, we're then going to start our application. We're then going to read runtime configuration, and this is a bit contentious, or has been in the past. I don't know if that's changed, but we'll talk about that in a bit. And then we're going to proceed to the next level. So this is sort of layer 0. Once we get an application up and running, what can we do? And we need to do the bare minimum to get the application up and running in a good state. We need to talk a little bit about mixed config versus runtime config. Lots of people have talked about this. I think some podcasts have talked about this. We actually felt so strongly about this at Latote before the diaspora of the Latote Elixir team that we actually wrote this up in our getting started docs and just said, don't use them. For anything involving runtime configuration, you should not use mixed configuration. I still stand by this. I think other folks feel the same. Because by and large, when you need to configure stuff at runtime, you're not really talking about internal Erlang stuff. You're talking about things like your Phoenix endpoint and your Ecto connections and those sorts of things. So the very first thing that we're going to do when we start this, when we start our application, is we're going to define what sort of configuration we care about. For instance, the port that we're going to run on and the database URL that we're going to talk to. And the very first child process that we're going to start is our config process. Our config process is very simple. It's just a gen server that takes your desired config, starts up an ets table, loads your configuration in, stores it inside the ets table, and if it can't load that configuration, it halts your boot process. Because you don't actually want to boot if things can't be configured, right? You don't want to boot your application with some level of assurance that you've actually pulled in the config values that you need. Loading our configuration is just a recursive function. We're going to try to, in this case, we're going to load it from system.getinf. But you could really do this from anywhere. At this point, you can start to pull things from etcd or vault or whatever other parameter store, whatever other configuration stuff you have. The nice thing about this is you're not constrained by this. And because you own all this code, you get to decide how you handle failures. So in our case, we're just retrying with a little bit of like back off. But you could do really whatever you want. And like I said, the nice thing about this is if you can't pull your configuration in there, you immediately halt the boot process, and you can figure out why. This is actually such a common pattern for us that we're trying to pull all this, kind of these ideas into a repo that we call Vapor. It was originally titled that because it was just vaporware. It's not anymore. It exists. And it's a real thing that can help you do some of this, and it has some other niceties around doing live updating of that environment. So now we've got our stuff booted, so we need to start our dependencies. And these are going to be things like our Phoenix endpoint and whatnot. So one of the important points here is that The app does not exist in a vacuum, and the app exists within a larger system, right? The larger system being things like your load balancer and being operators. And so at this point, what we're ready to do is start to put that application into the load balancer and say, like, are you healthy yet? I mean, this is equivalent to, your readiness and liveness checks. So we'll just pretend there's some up endpoint, and if that all works, it goes well. And if it doesn't work, we're going to send out alarms to operators. So the very first thing we need to do is start up Phoenix. Oops, that clicked through that. We're going to start up our Phoenix server. So what do we need to do that? Well, what we'll do next is add our endpoint to our configuration for our children. That's booted up after we've got our configuration. And then we can go ahead and start the endpoint. Phoenix, as many of you probably know, gives you this really nice init callback where you can sort of define the things that you want. At this point, we can ask it. We can ask our config for the port because it's already up and running. And we can then update the internal Phoenix configuration for this. And finally, what we're going to do is we're going to have a up controller that's going to allow us to figure out if we're up and running yet. And so this is going to allow our load balancer to pull our application and say, hey, do you have everything you need booted? And are you ready to start accepting traffic? And in this case, we're going to default it to 500 because we're not. We haven't started up all of our external systems yet, which is what we're going to do now. So once we're ready to connect to external systems, we can go back to our supervision tree. What needs to be started here? Well, at this point, we'll have a database we need to connect to or some other external service like this. We'll start up a database worker inside of it, which in turn is actually probably going to be something like a pool supervisor. It's actually going to be some other supervision tree, which is going to start a number of connection processes. And these processes are all going to start in disconnected mode. This is something I see people, when they first come to Elixir and Erlang, struggle with a little bit. But it's really, really important that we start these processes in disconnected mode. We start them without any assurance that the thing actually exists and is up. And the reason for that is because supervisors are about guarantees. Supervision is about providing a sort of baseline level to your whole application. So when these things come up, they're not going to connect to the database. They're going to attempt to move into a state where they try to connect to the database, and that may fail because maybe the database is overwhelmed. Maybe we're auto-scaling and we've added a bunch of new boxes, and the reason we're like auto-scaling is because the underlying database is overwhelmed with traffic right now. So they may not actually be able to connect. They may keep continuing to try with some sort of back off and jitter, and eventually they will be able to connect, and at that point we can start accepting real traffic. The way we can handle this inside of our Gen server, again, is simply to start up the application. We're just treating this as like a very simple state machine. We'll send ourselves a message in 3 seconds to try this again. And we'll do the connection inside of here and continue just to loop through that over and over again. If that works, we move into a connected state. Otherwise, we back off with some jitter and we try again. So now, once we've got all of those things connected, we can start actually providing feedback to our operators. So let's talk a bit about that. If when you're booting this thing, you can't connect to the database for some reason, if things are going wrong, we need to let people know that that's happening. We need to let operators know that something is happening here that we can't control. And so we're already giving responses back to the load balancer, and that's the first thing we need to do. We want to either take these systems out of the load balancer if they can't talk to the database, or we want to not put them in there to begin with. So we're going to update our status check just a little bit. And what we'll do is we'll call a simple database and database call and do a check status here. And we'll look for, it's an OK. We can say 200 and start accepting traffic. And if not, we'll say 500 and stop. In order to actually sort of monitor this correctly, we'll talk about that in a second. So that's the load balancer side. That's the technical side. We also want to provide feedback to operators in this case. And so we're going to use one of my favorite things in Erlang that I don't feel like gets talked about enough. But we're actually going to use alarms. So what we're going to do is we're going to split out a new process, which we're going to call a watchdog process. It's going to sit there and monitor our database connections and make sure we're up and running. And it's going to be a very, very simple state machine. It's going to check the DB status and either move from a good to bad state or move from a bad to good state. Keen-eyed observers in a minute will note that this is not a complete state machine diagram, but that's okay. If we move from good to bad, then we want to open up an alarm. And if we move from bad to good, we want to close that alarm. And that's a way that we can let external systems know what's going on. So this is going to be a fairly simple state machine. We're just going to use a gen server again. You could use gen statum if you want to, which I would recommend, but it doesn't fit on this slide if you use gen statum, so I didn't. You start up in sort of a degraded mode. You say that the number of passing checks is going to be 0, and then we're going to schedule a new check. When we check the database, we'll check status. This could be as simple as calling select one from your Postgres instance. It could be whatever you need to do to check to see if those connections are up and running. And based on that status in the current state, you're going to change your state, schedule another check, and then keep moving on. Change state is going to take the status and the count. If our result isn't okay and we're in a connected state, then we'll potentially clear any alarms that we had. We're using a thing called, a very fancy term called hysteresis here. So we don't clear and set alarms based on, we don't flap alarms too often. We'll wait until we see at least 3 good connections in order to clear that alarm. And if we're in degraded mode, we move back to a connected mode. If we're in a connected mode and we get an error, then we want to throw the alarm. And we're going to use alarmhandler.setAlarm. This is a thing that's built into Erlang. It's just available to you as part of the Sassel library, or application as we call them. So once we have that alarm set, if we're still in the graded mode, we just continue looping through that. So the things I want to really call out here are these 2 functions, alarmhandler.clearAlarm and alarmhandler.setAlarm. These things are really, really great because they allow you to sort of trigger these alarms from any pieces of your subsystem that you need. And the way that you take advantage of that is by implementing a gen event handler. So back in our application, we can swap out the standard gen event alarm handler, which I think just logs stuff to your error log. We can swap that out with our own custom alarm handler. So what we're going to do here. The alarm handler is, like I said, just a, you just need to handle, you need to have some handle event clauses. And if you set the alarm and it's the database is disconnected alarm, you can do whatever you want in here. You can send the alert to Slack or like Page Ops Genie or send it to Datadog or black hole it because you don't care. You can do whatever you want in here. Spam your coworker's email, whatever you want. So, and you can also handle the clear alarm as well. So if you want to send a recovery or do some follow-up stuff. The really rad thing is, like, this is just Erlang and Elixir code. So if you want to do some sort of remediation throughout the rest of your system, you could do that. Like, I mean, you're really unencumbered here. You can really choose whatever you want to do, which I find to be a very, very valuable pattern. So that was alarms and feedback, and that's how we kind of get information back out to our operators, to those people who are really working to keep our systems healthy. And finally, we're going to talk about communicating with services that we don't control. So we talked a little bit earlier about having a client that talks to our application that talks to some sort of downstream service. And as is the case with all downstream services, occasionally these things go wrong. And when they go wrong, they have a high likelihood of propagating that error back to us and back to our clients. And whether or not we get overloaded or not is sort of, it's an interesting question. But in any case, even if we're not getting overloaded by these requests, we're still not able to provide a reasonable service to our other external clients. And again, our clients are who determine if we're up or not, right? They get to determine that. They get to determine the method of failure. So what we often end up doing here, and this is not necessarily a revolutionary idea, this has been used and talked about in lots of different places, is we'll use some sort of pattern like a supervisor, or like a fuse or a circuit breaker. So that when these things do start to go wrong, we can start to figure out what to do in this situation. So the thing that we like to use a lot, the tool that we use, the library we use a lot for circuit breaking is Fuse. It's a fantastic library, very, very well tested, very, very it's highly optimized. It's great. Can't say enough good things about this library. You should totally use it for these kinds of operations. And what you get to do is you get to ask Fuse, hey, is this Fuse right here that I have? We're asking it in this case with the async dirty flag because this is in like some sort of critical path. We want to make sure we don't load down that request. Hey, is this thing still available? Is it still good? And if it is, then we'll go ahead and make the actual call. If it's not, we'll call fuse.melt, and after enough melts within a certain time span, we'll go ahead and return the fuse itself will blow, and we can start to return things like, hey, the service is actually down at this point. So that's great for stopping sort of the overload problem of where you're getting so many requests and so reliant on a downstream service that you eventually start to back up your requests because you're calling this thing over and over again that you know will fail. And that helps us solve that. But it also means that we can start doing all these other interesting things. And so depending on your liveness guarantees of your data, meaning depending on how stale that data can be, a pattern that we use a ton is to use a write through cache. And so what we'll do is we'll actually take any good request to the downstream service and write it into a nets table with some sort of key. And that way, in the case that this thing is down, the circuit will eventually blow, and we'll just start reading from the ETS table. And it turns out, actually, that this is way faster than actually going to the normal service, which is interesting. So this is, provides you an extra level of resiliency, but it comes at the cost of consistency. It comes at the cost of your data being correct, because you don't know, things may have changed in that downstream service. Turns out that's an okay trade-off for a lot of use cases, but you do need to go into that sort of clear-eyed. So circuit breakers are great. They're also a little bit of a sledgehammer because you're shutting off all of the traffic. And that often leads to these situations where you shut off all the traffic to the downstream service. The downstream service starts to come up and starts to heal again. You start to realize that you can make good requests to it. You turn all the traffic back on, and then the downstream service fails again because it hasn't fully recovered. You do get into those sorts of situations. It's not fun. And you get paged at 3 in the morning. It's very, very uncool. So we're actually pursuing some other interesting ideas using what TCP uses for congestion control, which is additive increase and multiplicative decrease. And we're actually looking at the new Mint HTTP adapter, and we're doing some interesting things with being able to adaptively figure out how much load we can actually put on a downstream system. So if you're interested in that, I would love to talk to you about some of the ideas that we've had. So that's it. We did it. We booted our application. Now what? Like, it took us 30 minutes to talk about how to boot the application. I thought this was kind of already a solved problem. And what we said we wanted to do was actually solve all these goals. Systems should handle failure gracefully. They need to provide feedback to their systems. They need to give insight to operators. Well, it turns out if you think through this stuff and you think about the ways in which you need to boot your application and the guarantees that you're going to provide at each level, then handling failures becomes a thing that you just have solved already. Because if your database connections go down, well, your load balancer already starts to know about that stuff, and you can take it back out of the load balancer, start figuring out ways to do that. Your operators are going to already find out about these things because you're going to provide feedback to other systems, and you're going to give insight to them via alarms. And so it turns out if you get this stuff right, you actually solve a whole host of problems for yourself right out of the gate. And I just think that this is so cool. Like, this is the thing I get really, really enthusiastic about this runtime. It's why I love Elixir. It's why I love Erlang. It's why I'm still here after however many years now. Because we have so many powerful tools in our runtime. And the main thing that I want you all to walk away with today is just the knowledge that you can take advantage of them and build more robust systems, go out and build awesome things, and enjoy the rest of the conference. Thank you.
Thank you very much.